There are 7 properties of exponents. They're kind of tough to keep straight, so I'm going to go over an example of each one before we go over the rule. The power of powers property works this way. If we have a base raised to a power, and that is raised to a power, we have a power raised to a power. X cubed is really x times x times x. And squaring something means that I'm going to multiply it by itself. So I'm going to have x times x times x times x times x times x. Or if I simplify that, x to the 1, 2, 3, 4, 5, 6th power. In general, my shortcut would be to take my base, and when I have a power raised to a power, multiply those powers together. So my rule for power of powers is a base raised to a power raised to a power is that base with my powers multiplied together. Product of powers. If I have the same base, x cubed is really x times x times x. X squared is x times x. And between those two bases, I have multiplication. So if I were to simplify that, I would have x to the 5th power. If you look, this is really x cubed times x squared. My shortcut would be to take my base and add my exponents. So the rule for product of powers. When I have the same base and I'm multiplying between those bases, I keep my base and I add my exponents. Quotient of powers. In order to do the quotient of powers, I'm going to have a quotient. I'm going to have division. So if I look, I have x to the 5th power as my numerator. I'm going to expand out x to the 5th. Over x to the 3rd power. Whenever I have x over x, that just is 1, so I can cancel it out. So I can cancel out 3 x's in my numerator and 3 x's in my denominator, and I'm left with just x squared. My shortcut would be, when I have the same base, top and bottom, I can just subtract my exponents. The quotient of powers rule. When I have the same base in a numerator and a denominator, I can rewrite that as that base with my exponents subtracted. And I have to take my top exponent minus my bottom exponent. Product of powers and quotient of powers are very related. The difference is, product of powers I'm multiplying, which means I add my exponents. Quotient of powers I'm dividing, which means I subtract my exponents. Power of a product. In order to do the power of a product, I have to have two things being multiplied together, like 3x. And I'm going to take that product and raise it to a power. So 3x squared is really 3x times 3x. Well, if I rewrote 3x times 3x as 3 times 3 and x times x, I'm going to really have 9x squared simplified. So my shortcut would be to distribute this squared to the 3 and to the x. And I can distribute because I'm multiplying between those two numbers. I can distribute exponents over multiplication. 3 squared times x squared, which is 9x squared. So the rule for power of a product is when I have two things being multiplied together inside of a grouping symbol raised to a power, I can distribute that power to both things and keep the multiplication sign between those two numbers. Power of a quotient. Similar to power of a product, but I'm going to want a quotient. So I'm going to want to divide my two numbers and raise that to a power. Well, x over 3 squared, squaring something means multiply it by itself, so I really have x over 3 times x over 3, which when I multiply fractions straight across, I end up with x times x over 3 times 3. My shortcut would be to take my quotient raised to a power and distribute that power to both the numerator and the denominator. I can distribute exponents over division. So I end up with x squared over 3 squared, which simplifies down to x squared over 9. So my rule is, when I have a quotient raised to a power, I can distribute that power to both the numerator and the denominator. These two properties are very related. I'm distributing my power over a multiplication sign and a division sign. And I can distribute powers over multiplication and division because they're next to each other in the order of operations. The negative exponent property. When I have a number raised to a negative exponent, normally raising 3 to the second power would give me a bigger answer, 9. But if I'm raising it to a negative 2 power, I need to get 9 smaller. So how do I get smaller? Well, I'm going to get smaller as a fraction. In order to get this exponent positive, I'm going to bring this whole thing down into the numerator of a fraction. I'm going to keep my base 3. The only thing that's going to change is my exponent. And my exponent is going to go from from negative to positive. And this was over 1. So I'm going to put my 1 in my numerator now. So I've dropped this into my denominator and switched my exponent from negative to positive. So I really have 1 over 9, or 1/9. So 3 to the negative power, negative 2 power, is not 9, but 1/9. If I start with a negative already in my denominator, it's kind of like a negative negative. To get this exponent positive, I'm going to bring this whole thing up into my numerator. So I'm going to bring this up and make it 4 to the third power. And 4 to the third power is 64. In general, the rule for a negative exponent if I have a negative exponent in my numerator, to make this exponent positive, I drop it down into my denominator. If my exponent is already negative in the denominator, I bring it up into the numerator to make it positive. And the last property, the zero exponent property. If I have 3 raised to the 0 power, my answer is not 1, it's actually, it's not 0, it's actually 1. If I have 3 to the 0 power, I really have 3 to the first over 3 to the first. Because 3 to the first over 3 to the first, if I use this quotient of powers property, is 3 to the 1 minus 1, which is 3 to the 0 power. So 3 to the 0 power isn't 0, it's actually 1, because 3 over 3 is 1. The zero exponent property says this: any base raised to the 0 power is 1, as long as that base is not 0. Let's look at a couple of examples where we have to simplify the expression using these properties. In problem number 1, I can start this problem multiple ways. The way that I'm going to start it is by getting rid of these parentheses. To get rid of these parentheses, I need to distribute this squared to the 7 and to the b to the negative 3 power. So when I distribute this second power, I'm going to get rid of the parentheses, and I'm left with 7 squared times b to the negative 3rd power squared times b to the 4th. 7 squared is 49 times b to the negative 3rd power to the 2nd power. Whenever I have a power raised to a power, I need to multiply those powers together. So I have 49 times b to the negative 6th power times b to the 4th power. Well, now I have two bases being multiplied together. And when I have two bases being multiplied together, I can use the product of powers rule. The product of powers rule says keep my base the same, but add my exponents. So I have 49 times b to the negative 2 power. Well, now I have a negative power. To get rid of that negative power, I need to drop that negative power down into the denominator. So it's 1 over b to the positive 2 power. And my last step, multiply those two things together. 49 over 1 times 1 over 49 squared is 49 over b squared. I know that I'm done simplifying when I have one fraction, all my like bases are combined, and all my exponents are positive. So to tell if I've simplified enough, one fraction, all my like bases, all my b's are combined together, and all my exponents are positive. Let's look at example 2. Again, I'm going to start by distributing this power into my parentheses. I really have x times y squared. So I'm going to distribute this cubed inside the parentheses. Notice that this 3, this cubed, does not go all the way to this 3. So I'm going to have 3 times x cubed times y squared to the third power, all over 27 times x cubed times y to the negative first. A power raised to a power is a power of powers. I need to multiply 2 times 3, so I get y to the sixth over 27 times x to the third times y to the negative first. Now at this point, I'm going to break this apart into fractions of common bases. So my first fraction is going to be 3 over 27 times x to the third over x to the third times y to the sixth over y to the negative first. The reason I do this step is so now I can combine my exponents. 3 over 27 simplifies down to 1/9 times, I have the same base top and bottom. When I have the same base top and bottom in a fraction, I need to subtract my exponents. Times, same base, numerator and denominator, subtract my exponents. Notice that it's 6, my top number, minus -1. So I simplify down. 3 minus 3 is 0. 6 minus -1 is 7. One ninth times x to the 0 power is 1, which makes sense. X to the third power over x to the third power is 1 times y to the 7th. Now I just need to multiply all these together. 1 over 1, y to the 7th over 1. 1 times y to the 7th power is just y to the 7th over 9 times 1 times 1. I know that I'm done simplifying because my fraction, I have one fraction in lowest terms. My exponents are all positive, and all my like bases are combined. Up here, I could have done this problem differently. If I wanted to, I could have taken 3 over 27 and rewritten it as 1/9. And then I could have said x to the third over x to the third cancels. And then I could have taken this y to the negative first power and brought it up to make it positive, which would give me 1 times y to the 6th times y to the 1st, which simplifies down to y to the 7th, over 9. Either way, I get the same answer. So it doesn't matter which property I use as long as I do the math correctly. When I was going over the properties, I did make one mistake. In the power of a product property, I distributed the m to the a and to the b, but wrote this letter as an n. Make sure in your notes that this second letter is an m, not an n.